Assalamu alaikum, welcome to second chapter. Here we will use overall heat transfer coefficient. Okay, so we have U, capital U, which is overall heat transfer coefficient. When you calculate it by, multiply that with A and delta T, you get the heat transfer as watt, okay, as a unit of watt. But how do we calculate overall heat transfer coefficient? You get multiple resistance, okay, multiple heat resistance, then you get minus 1, power of minus 1. And for this example, we have a series of conductive materials. So here we just add resistance, okay, resistance 1 plus resistance 2. But how do we calculate the resistance? If we just here write conductive resistance is proportional to length. More the length, more the conductive resistivity. And more the conductivity, we have less resistance, okay? So when I increase the conductivity, resistance will be less, okay? Because material allows you to transfer heat easily, but we are talking about resistance of heat transfer. That is like being resisting against the heat transfer, okay? So it is inversely proportional to the conductivity. So here what we have as R1 and R2 is just L1 over K1, then L2 over K2, okay? We should sum them, then take the power of minus 1. So let's calculate overall heat transfer coefficient first for this problem. And before that, maybe we plot the problem domain. It will be good to give an idea of the shape that we have. We have two layers. First layer with a known thickness, which is 2 centimeters. Here I don't know the thickness, okay? Thickness here, T is not given. I want to calculate the insulation layer thickness that I need in order to get a specific heat loss value, okay? So this is like a design question. So how much thickness I need for maintaining a specific value for heat loss, okay? So let's see what we have here. Okay, L1 is just 2 centimeters, 0.02 over K1, which is 1.3 watt per meter degrees of Celsius, then plus L2, I don't know L2, over K2. K2 is just 0.35. It's like insulation. So here you have more conductivity, but here is less conductivity since it's an insulative layer. Here meter times degrees of Celsius. So that means we have an unknown here at the term U. But if we keep going, so put Q, we know Q. It is like 1830. Okay, assuming that inner and outer surface temperature of the insulated wall. Here you have inner and outer. Okay, so that means delta T. Okay, insulation. Inner and outer surface temperature of the insulated wall. Okay, insulation layer. I thought if it gives us these two temperatures, we only use this domain, but it's not reasonable actually to do that because we use overall heat transfer coefficients for only multiple domains. Okay, so we should have multiple domain, and this is what is given. Okay, insulated wall means whole domain from the wall and thick insulation layer. So you have inside high temperature like 1,300, and here 30 degrees of Celsius. So we have the delta T. Okay, we can calculate it from there. What about the area? Here, assuming, okay, this is given as that the loss per square meter. So that means this is not Q capital, it is Q over A. Okay, Q over A is given. So that's okay. Meter square, and that's equal to U A delta T. But A is gone to other side, so you have U delta T, okay? U times delta T. And U is given as what we derived, okay? So here you have meter, and you have 1.3 watt per meter degrees of Celsius. You have L2 over 0.35 watt per meter degrees of Celsius. This is power minus 1, and you have temperature gradient. If we look at the units, here you have meter, but this meter also go up. So let's find overall unit of this part. It will be meter square over watt times Celsius, right? Okay, let me see. Meter square times Celsius. Celsius also will go up, okay? And when you get power minus 1, that will give you watt per meter squared times Celsius. Okay, that will be flipped, so that will give you this one, and this Celsius actually will cancel that term, so you have watt per meter squared, the same as this value. So that means if you take this L2 as a meter, what you get here, like if you plug in all values and calculate for L2, you will get as meter units. Okay, so let's use the calculator and see how we get the value. That's equal to something power minus 1 multiplied by 1,300 minus 30, and here we have 0.02 over 1.3 plus x, I don't know this L, over 0.35. Shift solve, and okay, so 0.2, let's say 4 meter. That means we need 24 centimeter of thickness, okay, for insulating this wall. I hope you got the idea how we calculate overall heat transfer coefficient for multiple conductive domains. And in the next examples, we see also how we combine with conductive and convective domains. So see you at the next video. Thank you for watching.